Hello, today we are going to discuss first order Stark effect in hydrogen atom. When an atom is placed in a uniform electric field, the energy levels are shifted. The shifting of energy levels produce a splitting of spectral lines called Stark effect. So if you read these sentences carefully, suppose when we are placed an atom in a uniform electric field, uh, the energy level of atoms are shifted. Okay, so the shifting of energy levels produces splitting of spectral lines. Such type of effect, first of all, observed by Stark, then we can call the Stark shift. Okay, which was the first observed by the Stark in hydrogen atom, especially in 1913. Okay, which was first observed by Stark in hydrogen atom in 1930s. If you spend little bit time to understand this effect a little more elaborate, consider an atom situated at origin. Let an electric field E is applied along the positive G axis if R is a radius of position position vector of electron. For example, if R is the position vector of the electron, the dipole moment, especially the electrical dipole moment, okay, not dipole, electrical dipole moment. What is electrical dipole moment? So this atom, nucleus is there, the hydrogen atom, okay, that is one. So around this one is electron is there, this electron, okay. So from here to here, the position vector of this electron. Now electric dipole, if you place this atom in electric field, this is a, for example, this one is uniform electric field, okay, uniform electric field is there here. So I don't want to mention here these lines, okay. So then I can use this line, okay. This is the uniform electric field, for example, uniform electric field. So the dipole, electric dipole momentum of this atom is mu equal to minus ER, right? Interacts with the electric field E, gives an additional potential energy levels uh, to this electron. Okay, the electric dipole momentum, this one is electric dipole momentum, mu equal to ER. This electric dipole momentum interact with this electric field E, giving an additional potential energy to this electron. So I'm going to write the Hamiltonian of this situation. Maybe you are all aware of electric dipole momentum, right? Minus mu E. So I'm going to use just G axis here. Okay. that equal to that equal to ER. Angle is cos theta, right? E cos theta. Therefore, we can use this one like this. E. Okay. This is electric field. This is G axis, Z component, right? R cos theta, G component. So now here, if you want theta value, theta is angle of position vector makes with the G axis. So the write Hamiltonian. I mean, modified Hamiltonian of this situation. So, in case if you remove this electric field, there is no electric dipole momentum interact with this electric field, and there is no generation of additional energy level to this electron. In that situation, that is a simple case, hydrogen atom. So I'm going to write that situation first. If you imagine here, there is no electric field. In that case, this is hydrogen atom. I'm going to write Hamiltonian of this situation first. That is minus h cross square divided by 2m. This means kinetic energy, potential energy of this hydrogen. Now, in addition, we are creating one new situation here. This hydrogen atom we are placing in electric field because of this electric dipole momentum with the interact with this applied electric field. Because of it gives the additional energy level to this electron. So then it creates a new potential between this electron and electric field, right? So addition energy level of this situation is E, well, applied electric field, G component or cos theta. This is very, very important information. By using this Hamiltonian, given Hamiltonian, we can calculate energy level of this hydrogen atom placed in electric field. Okay, this is all about explanation. Next step, we are going to calculate the energy levels of the uh, hydrogen atom place of uniform electric field. Here I am specifically mentioned uniform electric field. Remember that word, uniform electric field. That's it. In case if you further going to complicate thing, in case variational method or WKB method, you will get non-uniform electric field. Maybe I don't know. We can get the situation. Right now, we are in focus only this situation. So the ground state of hydrogen atom is in this situation is non-degenerate and the first order correction to the energy levels. The ground state only. Okay. So this better not to use this bracket. I have some more work is there here. So I need to give one more information. Okay. This is unperturbed Hamiltonian. This is perturbed Hamiltonian. First, we have to calculate uh, this energy level. Then we can add this corrected energy term. Okay. First situation is the ground state. The ground state of the hydrogen atom is non-degenerate. And first order correction to the energy is the first order correction energy n h perturbed Hamiltonian. This is the formula. So in our situation, we're going to use sorry. Sorry. Uh, Perturbation term E electric field or cos it into this wave function. So here I'm going to define this wave function like this ground state wave function. This is the ground state wave function. Okay, V e power minus r divided by a naught. This ground state wave function. Then you can use this ground state wave function here. Integral V e power minus r divided by a naught EER cos theta B e power minus r divided by a naught theta. Okay. Next, step by step, we are going to calculate this one. Observe carefully. 0 to infinity, 0 to pi, 0 to 2 pi. 0 to infinity is r. 0 to pi theta. 0 to 2 pi value. Right? So this situation is b square e power minus 2r divided by a naught e r cos theta. I'm going to use this one. In place of d tau, r squared dr sin theta d theta d pi. Write this one d tau equal to r square dr sin theta d theta d pi. Okay, volume. Okay, let us try to simplify this equation. First, this is b square 0 to infinity at the term e power minus 2r divided by a naught r square dr. Okay, 0 to 2 pi d pi integral 0 to pi cos theta sin theta d theta. Okay, see here, I'm going to simplify first this term. See here. This is I'm going to use sin 2 theta 2 sin theta cos theta, right? Then I can use like this 1 divided by 2 integral 0 to pi. I can write like this sin 2 theta d theta equal to, then you can apply integration. Sin theta is cos theta, then 2, 0 to pi, that equal to minus 1 divided by 2. This is cos 2 pi 1 minus, sorry, 0 to pi, right? This one is cos 0 1, cos pi, cos 2 pi also 1. This becomes to 0. Then entire this equation is come to 0. This is very, very important result. There is no first order correction to energy. Okay, then we need to check the higher order correction energy term. Can't leave like this problem. Then we can move into the higher order term. This is the most difficult task to calculate the higher order terms. In case if you come to whenever you face the second order and uh, second order correction energy terms, you will get more integration, difficult integration levels. Okay. So here there is no energy correction, first order correction. Then I want to know the higher order terms. So here I'm going to conclude this one. Hence, ground state hydrogen atom will not show a first order torque effect. This is very, very important. Okay. The first excited state n equal to 2 of hydrogen atom, we already discussed this two-fold, alpha-fold degenerate. Here we get four-fold degenerate. Is four-fold degenerate. We don't know this two-fold degeneracy, alpha-fold degeneracy, four-fold degeneracy. The previous class is there. Go and watch the previous class. You can understand what is the two-fold degeneracy, four-fold degeneracy, alpha-fold degeneracy. Degenerate. So since it has the L, M values, right? So the values I'm going to write here 0, 0, 1, 0, 1, 1 or 1 comma minus. Okay, LM values. L value 0, 1, 1, 1. m value 0, 0, 1, minus 1. Then these are the fourfold degenerates. Then the first exit state n equal to 2. Then we can write the quantum state, the specific quantum state. The four degenerate states may be conveniently be specified by the quantum number. N, L, M. Now you can understand what is this quantum state. Okay. Now we can use our first excited state number here. Place of n 2, 0, 0. Okay. First one. Second one 2, 1, 0. Third one 2, 1, 1. Fourth one 2, 1, 1. So this is fourfold degeneracy. Okay. If you apply this perturbation theory for degeneracy state, require the evaluation of 16 matrix elements of this uh, tetrabot term. The fourfold matrix are non-zero. Okay, since the corresponding the same parity. So, for example, if you get a odd diagonal matrix elements between the different values are zero. Okay, better to write these codes here. I'm going to write one note here. So as the state, this note is very, very important, as the state is fourfold degenerate. The application perturbation theory for degenerate state required the evolution of 16 matrices. 4 by 4 at 16 matrices we can get combination of these four. Okay. If you want to check that blindly 16 matrices, then you can try the 16 matrix integrations. No need to check all the matrices. Okay. Which is why I'm going to write this note. You can go blindly 16 matrix by using the traditional this perturbation theory. Then if you want to calculate that 16 matrix by using integration, then you will get the answer, but it will take time. Okay. By avoiding that long process, We need to go for some concept here. A very, very important parity concept. By checking parity concept, we can reduce the difficulty of this calculation. Okay, now we need to check all the trials, 16 trials. Okay, 16 matrix, elements of tetraploid Hamiltonian of these. The four first keynote, the four diagonal matrix elements are zero, since the correspond to the same parity. H prime is of odd parity. Okay, these are all zero. Remaining 10 also zero. Then I'll show you here the odd the odd diagonal matrix elements between states of different m values. This is very, very important. You can get almost 10 combinations here in 10 numbers are also zero, since this is the result parity. And check this one. M prime minus m, okay, pi d pi equal to 0 if m prime is not equal to m. This is the reason. So out of 16, actually we got 4 into 4, 16 matrices. Out of 16, 4 are diagonal matrices, the same parity, or get to 0. So remaining 10, 10 odd diagonal matrices in between state, different m values also go to 0. Then only two states are there. The remaining two states two matrix elements one is 200, another one is 210. Okay, and 210 I can say directly by skipping this explanation, but it's very difficult to say like that. Okay, this is the reason why we are uh, skipping these steps. Okay, you can get almost a 16 combination by using this four. Okay, only these two combination remains non-zero terms. But what is the reason behind the explanation is this one. One is the same parity, another one is the different values of m. Their combinations are going to zero. In case if you have any doubt, please go and try any one of the combination by using these two conditions. Then you will get the answer is zero. I'm sure. Okay, please go and try this one. Only these two terms, only except these two matrices, remaining all combination going to zero. The reason is this one. Now I'm going to check this energy character energy term. Only these two states. Okay. So for that I'm going to use here. So in this perturbation theory, you go to further explanation, then you will get a more complicated terms and more complicated calculations. More it is needed, required the more time to explanation these type of questions. Okay, so we want this 200 wave function. Then I'm going to use this type of okay 2 r divided by a naught e power minus r divided by a naught, and psi 210 wave function is c r divided by a naught e power r 2 divided by 2 a naught cos theta. So these are the wave functions. Psi 200 wave function. We already calculated this wave function by using the uh, hydrogen atom angular momentum unit. We already calculate these values. Solve the hydrogen atom problem, then you will get this type of equation, eigenfunctions of hydrogen atoms, ground state, first excited state, the next excited state values you can get. So where here the C is, where C is 1 divided by 4 root 2 pi 1 divided by a naught 3 divided by. Here on it is Bohr radius. Okay, so I'm going to use this information here. Okay, so for remove this one. If you observe here carefully, I'm going to calculate only one matrix. Remaining two other matrix I'm going to use to direct solution. So this is the final step. After that, we are going to conclude this topic quickly. So this is our task. First task 200 h prime. I mean Petrobottom 0. Okay. So this situation is wave function psi 200. Okay. E r cos theta. This is wave function psi 210. Integral 0 to infinity, integral 0 to pi, integral 0 to 2 pi. C 2 minus r divided by a naught e power minus r divided by a naught. So only psi 200 Here wave function is there. This is a wave function, right? And 210 wave function, this one. This is a perturbed term. Okay. I hope you are understanding what we are going to calculate. We are going to uh, calculate the perturbed term energy level. Okay. Keep remember that words. E power minus r divided by a naught cos theta. So this integration we are going to solve it. So everybody going to think this one is it will very difficult to solve this one. Not everybody. I'm not saying that votes everybody, but they are feeling this very by looking this integration. They get, oh, we can't calculate this one. That is wrong thinking. You can easily calculate this type of equation. Let's go and see this one. Any constant values are there here? C. Okay. Here this A is constant. Okay. C also constant. This is okay. E is square constant. All the remaining terms integral 0 to infinity term, which means r terms, 2 minus r divided by a naught, r term, this is r term. Here also r term is there, r term. Okay. And if, yeah, I forgot here, d tau also there. So d tau we can write, right? What is the d tau value? R square dr sin theta d theta, right? You can write. Yeah. So better to use here. I'm going to remove this one. You remember this one. Theta value r square. Extra term also there, right? Here theta volume. R square dr sin theta d theta d pi, right? This is the correct term. Okay. So theta value. I forgot to put theta value here. Okay. This is fine. Here r is there. Here r is there. Here r square is there. I'm going to use the term here, the r term. So please be focused here. R, here r is there, here r is there. R square, r cube, r power 4. R power 4 divided by a naught. And uh, yeah, this is one more mistake I did. 2a naught, right? See here, 2a naught. Okay. These are all r terms. These are all r terms. E power, e power, r terms. E power minus r divided by a naught minus r divided by 2a naught into dr. Okay. Next term is integral 0 to 2 pi d pi. Next term 0 to pi cos square theta sin theta d theta, because here this one is cos theta is there, here the cos theta is there, sin theta d theta. Okay, so we already know, right, this one. What is this value? 2 pi. And what about this one? uh, this integration I'm going to solve right now here. Okay, so okay, no problem. I want to solve this integration, right? 2 pi cos square theta sin theta d theta, cos theta equal to t minus sin theta. If you differentiate this one, minus sin theta d theta dt. Therefore sin theta and d theta equal to minus dt. So if you use integration theta is equal to 0, what will you get? First one, t equal to cos theta equal to 1, theta equal to pi, second integration, limit t equal to cos pi, then you can get minus 1. Okay, so minus, so I'm going to use this information here. Okay, minus integral 1 to 1 integration. After applying integrations, this term is t square, right? T square. Okay, d theta sin theta d theta minus theta minus dt. So if you interchange this integration values, limit value, then minus will go, right? I'm going to interchange this limit values, t square t theta. Now you can apply integration, t keep divided by 3 minus 1 1, then you can get easily 2 divided by 3. Okay, what is this answer? 2 divided by 3. So now we are going to simplify this one. So extra terms we'll get c square 2 pi and 2 divided by 3 also there. 2 divided by 3, remember. Integral 0 to infinity, I'm going to write this one, this equation term like this. Listen carefully here. 2r power 4 divided by a naught e power minus 3r divided by 2a naught minus r power 5 divided by a naught square e power minus 3r divided by 2a naught. Okay, into dr. No need to worry about this integration. Very simple formula is there. Integral, this is the formula. Integral 0 to infinity x power n e power minus ax dx equal to, okay, n factorial divided by a power n plus 1. So apply this formula here. So it's similar formula is there, this one. X power n e power, if you consider this one, 3 divided by 2a is a, then you can easily apply this formula. After applying this formula, see here, e E. This is C square 4 divided by 3 pi. Two divided by A naught 4 factorial divided by 3 divided by 2 A naught whole power 5 minus 1 divided by A naught square 5 factorial divided by 3 divided by 2 A naught power 6. Okay, this is the simplification. So if you simplify this one easily, then you can get answer here. Minus 3 E A naught. This is the first answer which we want answer. Okay. Two one zero. Sorry, not 210 term. 200. H prime 210 equal to minus 3 E A naught. So similarly, in case if you do this situation, to change this wave function, then you will get this equation A naught. Okay. So I'm going to conclude this topic. Take 10 more time, maybe 10 more minutes. Yeah. The, the perturbation matrix is therefore, this is perturbation matrix LM, right? 200, 210, 211, 21 minus 1, right? H prime equal to, okay, H prime 200, 210, 211, 21 minus 1. 0, these two terms 0, right? And 200, 210. You got answer, right? Minus 3 E A naught. And remaining all these terms are 0 except these two situations, right? 3 A naught. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. These are the 16 fourfold degeneracy energy levels, 16 matrices except 2 remaining all are 0. Okay. So here one is plus, I think. One is both I put here the minus. One is plus, one is minus. Check this one. Okay. Simplify this one. One is minus, you will get one. Another one is plus, you will. Okay, no problem. So the determination is then we can write like this. The secular determination secular determinant is then e to power 1, okay, 3 e a naught 0 0 minus 3 e a naught minus e to 1 0 0 0 0. This is 0 0 0 0 minus e to 1. This is determinant of this secular equation. Okay. The four roots of these determinant equations are equations are 3e a naught minus 3e a naught 0 comma 0 0 and final one is 0. One is plus 3e a naught, one other minus, remaining two are 0 0. The states 2 0 0 and 2 1 0 are affected by the electric field, whereas the states 2 1 1 and 2 1 minus 1 are not affected by the electric field. The four-fold degeneracy is those lifted partially eigenstates corresponding to these eigenvalues can be evaluated by using Cn divided by Cl equal to minus 1 and Cn square plus Cl square equal to 1 relation. Okay. So for example, if we take Cn equal to minus Cl, then Cn square plus Cn square equal to 1, then you can get Cn equal to 1 divided by root 2. Cl equal to minus 1 divided by root 2. The corresponding, the eigenstate corresponding to the eigen value 3 E A naught is this one, 1 divided by root 2, 2 0 0 minus 1 2 1 0. Okay, the eigen state corresponding to the eigenvalue minus 3 E A naught equal to 1 divided by root 2, 1 2 0 0 plus 2 1 0. So this is the torque effect. So this is, for example, our hydrogen atom. Okay, this is our hydrogen atom. When we place this hydrogen atom, okay, this hydrogen atom energy levels are split. The splitting of energy levels produce splitting of spectral lines. Okay, this is C2 0. This is E2 or 0 plus 3 E A naught energy level. I mean eigenvalues. Eigenfunction, this one, corresponding eigenfunction 2 0 0 minus 2 1 0. This is, there is no Stark effect, right? There is no Stark effect. Okay. 2 1 minus 1. E2 power 0. This is 3 A naught 1 divided is corresponding eigenfunctions 2 0 0 plus 2 1 0. Okay. This is the all about the Stark effect of hydrogen atom. This figure the energy levels wave function of the first excited state of a hydrogen atom in an electric field. So this is very, very important. Okay, so this figure energy, energies and wave function of the first excited state of hydrogen atom in an electric field. The hydrogen atom is the first excited state those possess the permanent electric dipole momentum of magnitude 3 E naught with different orientations, one state parallel to external electric field, one state is anti-parallel to the field, and two states with zero component along with the field. The states 2 1 1 and 2 1 minus 1 do not possess uh, dipole momentum and therefore do not have the first order interaction with the field. So I'm going to say again this one very very important conclusion, this explanation. The hydrogen atom in the first order excited state, those possess permanent electric dipole momentum of magnitude 3 E, I mean this one, 3 E A naught with three different orientations. One state is parallel to external electric field, one state is anti-parallel to the field, and two states with zero components along with the field. The state 2 1 1, 2 1 minus 1 do not possess dipole momentum and therefore do not have the first order interaction with the electric field. This is all about this first order torque effect.